Okay, what's up everyone? Welcome back to another fun day of proof, set theory, and logic. How's it going? Wednesday. Cool. So, last time we were talking a little bit about sets, talking a little bit about subsets, inclusion, all the good stuff, right? Let's start out with a quick little example. This is example 3.5 in the note packets. So, define the sets. Let's do A, which we'll do 1, 2, and 3. B, 1 to the set of 3 and 4. And C, to be 1, 2, 3, and the set of 4. Okay. Is it true that A is a subset of B? That's my question to get you warmed up today. True or false? No. Yeah, I'm seeing some thumbs down. Right on. Good. And why?
Because 3 is not the element of B.
Exactly. Exactly. No. 3 is in A, but 3, writing my 3 backwards, 3 is not in B. Remember, writing 3's in set brackets, I always get them mixed together. Remember that 3 is not the same as the set containing 3. One of them is an integer, one of them is a set containing an integer. Does that make some sense? Good. Okay. Now, is it true that A is contained in C, is a subset of C? Yes. Why? Because every element of A is an element of C. 1 is an element of A. 1 is also an element of C. 2 is an element of A. 2 is also an element of C. 3 is an element of A, and 3 is also an element of C. A and C, however, are not equal, since C contains an additional element, which is the set including the integer 4. Okay. Is B a subset of C? Yet again, no. Is C a subset of B? Yet again, no. And for effectively the same reason that A is not a subset of B, because a set containing an integer is not the same thing as the integer itself. Yeah? Basically, the thing to recall from last time is that set brackets do not function like parentheses. That is, well, if you have something like 3 plus 4 and you put it in parentheses, it's the same as 3 plus 4 without parentheses. And if you put yet another parentheses around it, it's still the same thing. Set brackets don't work like this. When you throw set brackets on something, it is creating a new object, if you want to think of it like that. When you wrap something in set brackets, you're creating a new set. You're specifying a new set that contains the things inside of the brackets as its elements. Cool? Parentheses, on the other hand, are just like a grouping tool, right? They help us know which things to do first. Okay, fun, easy enough. So, quick little definition. A subset A of a set B is said to be a proper subset if A is not the empty set and A is not equal to B. i.e. empty set not equal to A, which is a subset of B, but is not equal to B. Does that make sense? Okay. So proper subsets are something other than the trivial subset. Remember, the empty set is a subset of, well, anything. since every one of its elements is contained in any other set you pick. I guess that's vacuously true since it doesn't have any elements, right? If it were not a subset, then there should be some element in it, which you could say, hey, look, that's not an element of the other set. But there's no elements in it, so you can't do that, right? Hence, the empty set is a subset of every set. So it's not really an interesting one. Similarly, a set is a subset of itself, but yet again, it's not really an interesting one. The interesting ones are the proper subsets, if you want to think of it like that. Proper subsets are just the ones that are not the whole thing and not nothing, but something in between the two. Cool. All right. So quick question. Does a one-element set have any proper subsets? If a set just has one element in it, does it have any proper subsets? Nope. If a set has more than one element in it, does it have any proper subsets? Yep, always. Okay. If a set has two elements in it, how many proper subsets does it have?
Oh, just two.
Two. Yeah. So for instance, if your set was, say, 1, 2, then the proper subsets would be the set with just 1 in it and the set with just 2 in it. Anything else would have either no elements or all of the elements, right? Okay. Kind of a quick little question then. What about a set with 3 elements?
No, it's actually down.
1, 2, and 3. Well, you could arrange the 2-element subsets. You could have 1 and 2. You could have 1 and 3. You could have 2 and 3. Then you could do the 1-element subsets, 1, 2, and 3. And then you have the empty set at the bottom. And if you want to think of it like this is a subset of that, that's a subset of that, that's a subset of that. 2 is a subset of this one and that one. 3 is a subset of this one and this one. 1 is a subset of this one and that one. And the empty set is a subset of all of them. And if you look at it, it looks a little bit like a cube, doesn't it? Oh, that's kind of nice. Cool. So if you draw like the 2-element subset, or the set with 2 elements, a set with 2 elements, and you look at its subsets, it looks like a square, right? What do you think will happen? How many subsets, how many proper subsets does a set with, say, n elements have?
N factorial?
N factorial, you're saying?
2 to the n power.
2 to the n is a reasonable, yes, okay, I see exactly what you're saying. Yeah, so if you have a 2-element set, right, like 1, 2, and you have your empty set at the bottom, and you have 1 over here, you have 2 over here, something like this, and you're like, okay, how many proper subsets does it have? 2, right? Here I have 6. What's the pattern? You don't actually have to answer this right now, but a good one to think on. Can you figure out a pattern or structure? Could you prove a little formula for yourself about how many proper subsets an n-element set has? That'd be kind of nice. By the way, these kind of nice diagrams sort of giving you a depiction of the subsets inside of a set, defining something like an ordering on them, from the biggest one down to the smallest one, going in between, right? These are a type of diagram that if you study an area of mathematics called order theory, you would see a whole lot. But that's neither here nor there. We won't talk about that in this class. So fun. Just a good way to visualize things. All right, so we've got some sets. We've got some subsets. I think everyone is doing pretty good remembering what subsets are and how they work and what proper subsets are. We're doing great. Now, let's prove a theorem about subsets. So, theorem. Here's a little theorem about sets. If A is contained in B and B is contained in C, is a subset of, i.e., then A is a subset of C. That is, containment is transitive. If this one's in that one and that one's in the next one, then the first one's in the last one. Kind of collapse the middle terms. Does that make some sense? Cool. Okay. Should we prove it? All right. Okay. So how would you go about doing this? Well, to show that A is contained in C, we'll show that any element A in big A satisfies little a in big C as well. Okay. That's what it means to be a subset, right? A is a subset of C if and only if every element of A is also an element of C. So we'll pick an arbitrary element, and we'll show that that element belonging to A implies that it also belongs to C. All right, since the element was arbitrary, we are perfectly well justified in making a universal generalization and saying since it holds for anyone you want, it holds for all of them, right? Okay, so to do so, notice that if A is in big A, then A is in B via our assumption that A is contained in B. That is, that A is a subset of B. As B is a subset of C, a little b in big B implies little b is in C as well. So take, that's a K, take little b equal to A to deduce that A is in C. This is perhaps a verbose way of saying it. If you would like a shorter form way of saying it, here's a less wordy but perhaps more difficult to follow version. You could say something along the lines of like this. You could say, here, I'll perhaps write this off to the side. Let me move the camera. Okay, so if you want to do like a less verbose version of it, so you've got, you could do like a column type proof. Go, hey, A is contained in B, that's a hypothesis. 2, B is contained in C, it's a hypothesis. 3, taking some A and A implies that A is in B. This is the definition of 1. That's what it means for A to be contained in B. Yeah? This is the definition of 2. So if something is in B, then it also belongs to C. Okay. Then you can kind of take this from here and go, hey, look, we could instantiate something here. If I want to be actually fully precise, what I should say here is that for all A and A, I guess I can leave that number there, and for all B and B, we could pick, and basically what I'm going to say now is that you pick one of the elements of A, instantiate. we instantiate 3, and then we take from there, and we instantiate, we use this instantiation in the next one, yeah? So, we instantiate 4 with what our element was from 5. And now, to finish it off, since x is in A implies that x is in C, we can say that A is a subset of C. This is by definition. Do you see kind of the column-based version, which looks worse, right? Feels more complicated than just directly saying it. Perhaps all of this feels unnecessarily complicated. After all, if you've got some stuff and it's in another thing, and that thing is in yet another thing, then the first thing is in the other thing, right? It feels easy when you say it. So, okay, subsets, perhaps not crazy, perhaps not too wild, but all the same, something that it is very important to become familiar with. Now, you might ask yourself, you might say, okay, so if a lot of this is all about building up mathematics from like the foundations, right? If we're trying to say, hey, what do I need to get mathematics? What are the actual things I have to assume to create mathematics out of all of this? Well, you might ask yourself, hey, can we do everything in just one set in some sense? That is, could we make a universal set where we could somehow put all of our mathematical statements into properly encoded in some form? A good question, and something that indeed people have thought about quite a bit. So this is section 3.2.3, universal sets. So in many situations, we use I guess I should say, an overarching universal set, i.e. a set to which all elements, or all sets we consider are subsets of. Perhaps it's a weirdly phrased sentence, but basically the idea is like, hey, if we're talking about, regular old arithmetic or something like that, you might be like, oh, well, it says a solution that's like a regular number, real number, or is it like a complex number or something like that? A lot of the times in some of your previous classes, kind of the overarching universal set that you're talking about is either the reals or the complexes. Like in calculus, right? All of your, the answers you get out of things, the domains and codomains of functions are some subset of the reals, yeah? Or occasionally, some subset of the complex numbers, yeah? This is effectively a matter of convenience. That is, most of the time we do this, we just kind of assume this ambient universal set. It's basically just a matter of convenience. So you don't have to, be extremely explicit about which sets you're talking about at all times, right? That is, when you are in calculus and you talk about like x squared plus 1 as a function, you kind of implicitly treat it as the same function irrespective of whether it's defined on, say, like all the real numbers or on the open interval from -1 to 1 or on the closed interval from 8 to 11 or something like that, right? You have some sort of a sense that there's this like ambient universal set going on there. And so occasionally you'll see some sort of like reference to a universal set for whatever you're doing. This is a perfectly reasonable thing to talk about. But if you want to get at some notion of universal sets for all of mathematics, or for some portion of mathematics you care about, For the same reasons that we talked about when we talked about Russell's paradox briefly last time, there are issues with this. That is, whether or not these sets exist is not a thing that you get for free. So for instance, there's a concept, we talk about a Grothendieck universe, right? Where you want, maybe you never heard of that, probably not. But people will talk about like, hey, is there a set where you can basically model all of the mathematics you're trying to do inside of this set? And whether or not they exist is something that you would have to, either assume or deduce from your axioms. And so the question then becomes, what axioms allow you to deduce the existence of these things? Are they simple ones that you might expect, or do you need extra stuff, or do you just have to assume they exist? Or is their existence something that you can't say, perhaps, with a given axiomatic system in any conclusive way? Maybe you assume some stuff and it's like, hey, can I say that such a set exists? And the answer is, you can't say whether it does or doesn't with the things that you've assumed. It's a new thing. So there's a whole lot of nuance that goes on with trying to describe universal sets in the context of a more general thing than convenience, like when you're doing calculus. There are more foundational considerations, which we won't talk about at the moment, but something good to perhaps have in the back of your mind. Otherwise, I think people come away from classes like this with some sense that like, hey, there's just a big old set and everything lives in it, which maybe, but this is not a given, right? This has to somehow, you have to either be able to show that such a thing exists or start by supposing that it exists. It is not just automatically the case that you can put everything in big sets just from whatever axiomatic system you start with. So, okay, maybe that's like a slight digression, but something that is good to mention. We will talk about this more later. Okay, fun. Now, equality of sets is an easy one. So equality of sets is something relatively straightforward. And we will prove a quick theorem. So given any two sets, A and B, A equals B, that is, they have exactly the same elements, if and only if A is contained in B and B is contained in A. That perhaps makes sense. After all, A is a subset of B if every element of A is also an element of B, and B is a subset of A if every element of B is also an element of A. Putting those things together says that A and B have exactly the same elements, which is what we mean when we write A equals B, right? This will actually turn out to be one of the most powerful and valuable tools we have for showing that sets are equal, since usually it's actually sort of difficult to go through and show individually that they have exactly the same elements. That is, if our sets are not nice and small, like many of the ones I've been writing on the boards as examples, something like a genuinely large set, it can be kind of difficult to show that they have exactly the same elements, but it can be much easier to take some element from one set and show that it lives in the other, and then take some element from the other set and show that it lives in the first one. If you can do those two simple little things, then you've shown that they actually have the same elements. Yeah? Kind of nice. Okay. And this theorem I want to actually prove right here. It is a good one for you to think on if you don't see it, but basically follows the exact same type of reasoning as the last one. That is, we'll say, hey, take some A and A. Look, by this containment, it is also an element of B. Now take some B and B, and look, by this containment, it's also an element in A. So they have the same elements, right? That is, if they didn't have the same elements, at least one set would have an element that doesn't belong to the other, right? But you can really rapidly derive a contradiction via one of these two conditions. Yeah? Okay, cool. So I'll leave that, floating in the air for the moment, and move on to section 3.3, which is operations on sets. So that little diagram I drew earlier with the subsets of a finite set, I want to actually kind of return to really quickly as a little sketch of the idea for you. So here I'll do just 1, 2, and 3 really quickly. Then I'll do 1, 2, 1, 3, and 2, 3. Then 1, 2, and 3. Then I'll draw my little lines. And what I want you to notice looking at this, which is, I think, like a reasonably sensible diagram, you can sort of say like, hey, is something a subset of something else? Well, can you follow the lines up to it? Yeah, reasonable. I want you to notice that there's actually hidden in here a sort of arithmetic of sets. Just from this picture, you can actually see two kind of cool ways to put sets together. That is, pick two sets and follow the line together up, and you get a new one, right? Pick these two and follow the line between them up, and you get a new one. It tells you something basically along the lines of, hey, you can put things together. Take, say, like this set and this set. Follow the line, say, down, and hey, there's a new set. Take this set and this set, follow the line up. Hey, there's a new one. What I want to point out is that these are actually really, really interpretable, easy operations. What happens when you follow the lines up? Yeah, exactly. You put them together. So if you take 2 and 3, and you follow the lines up, you get the set containing 2 and 3. If you take 3 and 1, 3, and you follow the lines up to like their meeting point, you just get 1, 3, right? Okay, so this sort of operation of going up the lines is just putting sets together, putting the stuff from the sets into one set together. Think of it like the set is a bag containing things. If you take 2 bags that's got some stuff in them, and you just dumped everything out on the floor and you put it in one big bag, this is an operation you can do on sets. You can take 2 sets and form from them a new set by taking a set that has all of the elements in the original 2 different sets. Yeah? Similarly, you can take 2 sets, you can dump all of their elements out. If they're like bags of stuff, dump all the stuff out, and then look through each pile and take only the stuff that you get in common between the piles. This is the going down. 1, 3, and 2, 3, if you go down, you just get 3. That's the only element that they have in common. Oh, okay, kind of nice. If you want to picture this like Venn diagrams, this is like where like the circles overlap, right? While going up is like taking both the circles at the same time. Okay, so hidden inside of a simple kind of diagram like this, you actually get immediately some sort of a notion of, I don't know, I want to say addition perhaps, and something kind of like subtraction, not exactly. What it actually corresponds more closely to is some of the logical operations we did with propositions. Oh, let's look at it. So here is the definitions we will throw out. The first definition, the union, as we call it, of 2 sets, let's call them A and B, is the set denoted A union B, big old U, usually drawn without a tail on it, right? Big old cup, which is defined to be the elements X such that X is in A or X is in B. Okay. Likewise, we can define the intersection of 2 sets. So definition. the intersection of two sets A and B is the set A, and since this is kind of like the same thing as the union, but instead of going up, we'll go down, what could we use to denote it? Maybe we could use the same symbol, but we can make it go down instead of up, yeah? A cap, A intersect, A upside down U, B, which is just a set of x's such that x is in A and x is in B. Oh, it's almost like you can see that this symbol and that symbol, they look really similar, right? One of them is just a little bit pointier. This symbol and that symbol look really similar. One of them is just a little bit pointier. Oh, cool. It's the same concept, right? You can see where the notation comes from, I guess. Perhaps it's not any sort of a real revelation that there's something cooler going on underneath, even though there is. It at least makes it a more intelligible notation, yeah? Cool. All right. What I want to also kind of point out with all of this is that you're seeing your first hints here. Like, while this might seem like something totally simple and easy, what I want you to pick up on is you're seeing your first hints here of orderings on sets, like ways to arrange things so something you can see as bigger or smaller. And these orderings are actually really nice because they come from operations that you can do on things. That is, if you take the union of two sets, you get a set for which both of those sets are subsets, right? That is, if you think about it, R is a subset of sign. It looks kind of like the less than or equal to sign, just a little bit less pointy, yeah? So we probably have a notion of ordering on subsets of a set. That's the levels that we drew on the board when we did that diagram. And this ordering is, you're going to think of it, it's like an algebraic ordering. That is, something is bigger than something else if there is another subset such that if you union those two things, then you get the bigger thing. Does that make some sense? That is, A is a subset of C. This is something you could prove if there exists some B such that, which I'll abbreviate ST, A union B equals C. Does that make sense? That is, if every element of A is an element of C, what is the subset that you have to union it with to get C? It would be all of the stuff that's in C that isn't in A, right? B would just be a set of x's in C such that x is not in A. Yeah? Oh, so in some sense, there's an order relation that is induced by an operation on pairs of things. Nice. You can imagine the exact same business holds for something like, less than or equal to's, right? Where you say like, hey, like 2 is less than or equal to 4 because there is some positive or non-negative at least number that I can add to 2 to get back 4, right? The difference between them is non-negative, yeah? 4 minus 2 is 2, yeah? So the exact same type of thing happens in familiar situations. Maybe this is not too immediately interesting to you guys, but I guess I'm trying to show you that many different concepts that you've seen in different places, how to take two things and put them together to get something new, how to line things up in a row, even ways of talking about how close things are, all of them kind of overlap. That is, as soon as you have a way to talk about things being close together or far apart, you have a notion of some things being closer or farther, you have an ordering. And as soon as you have orderings, you have some sort of a way, perhaps, if you've got a notion of closeness, to build a operation to put things together. And whenever you've got an operation to put things together, you immediately get orderings. And whenever you have orderings, you immediately get a notion of closeness or farness apart, right? Like, if you've got a set that's a subset of another thing and there's no intermediate subsets, no proper subsets that are bigger than the small thing and smaller than the big thing, then they're about as close as they can be. Yeah? And so, okay, we've immediately built a notion of closeness. Somehow all of these things are tied together. That is, as soon as he's talking about whether or not things are similar to each other or not similar to each other, you've automatically ordered things. As soon as you start trying to put things together in any sort of a nice or coherent way, you've automatically created a notion of similar, and you've automatically ordered things. It's kind of crazy, yeah? You get a lot of structure from almost nothing. Really fun. So, all of the ways these things play together, these kind of basic concepts of ordering, closeness, some notion of like an arithmetic-like operation, all of these things start to interact with each other, and most of that is what we end up exploring. How do the order theoretic properties interact with the, what we'd call, I guess, like topological properties, notions of things being close together, stuff like that. Yeah, cool. So we'll get to see all of this. So let's do a quick example, just to make sure we get unions all good. Let A be the set 1, 2, 3, 4, and 5. And let B be the set 2, 4, 6, 8, 10. Then A union B, a big cup B, is what? Well, it's the set of all x's such that x is in A or x is in B. So, which things are in both A and B? Well, 1 is in A, but it's not in B, is it? So 1's not in there. 2 is in A, 2 is also in B. 2 would be in here. Oh wait, sorry, union, I'm doing intersection. Oops. So 1, 2, 3, 4, and 5 come from A. Now, the stuff that's in B also has to come over as well. We've already got 2, we've already got 4, but we don't have 6, 8, or 10. Okay, there we go. So A union B, and that's not a 3, that is a closed set bracket, which is always remarkably hard to draw. There you go. That's everything that's in both A and B. Or A or B, I guess, sorry. Sometimes when we say and colloquially, we mean it as like both things, but not, yeah. Okay, while A intersect B, well, this is the set of all things that are in both A and B. Not one or the other, but in both. So 1 is in A, but it's not in B, so we won't get 1 in the intersection. 2 is in A, and it is in B, so we will get 2 in the intersection. 3 is in A, but 3 is not in B, so we won't get 3. 4 is in A, and 4 is in B, so we will get 4. 5's in A, but 5's not in B. Wow. Looks like we don't get 5 in there. Now what about 6? 6 is in B, but it's not in A. 8's in B, but it's not in A. 10's in B, but it's not in A. So it looks like the full intersection is just 2, 4. Cool. Right on. You can imagine, which I will not do, you could write out all the numbers 1 through 10, and you could draw the relatively titanic diagram like we did with the 3-element subset. And you can imagine just taking this one and following to the closest line together, which would be this set. And you could take these two and you could go down to the place where they intersect, which would be this one. Yeah? Follow down to the closest common point of intersection. Nice? All right. Pretty cool. So unions and intersections, hopefully we are feeling good about them. Now, what can we do with all of it? Well, as soon as I erase this board, we will see. One thing that is perhaps worthwhile to note is that I guess in a certain sense, a little bit of our notation here is, I don't know, perhaps slightly abusive, I guess. I don't know. We've done something actually a little bit bad, I guess I'll say. which comes back to something we talked about a moment ago. That is, actually, yeah, I'll point back over to this board quickly. Notice that when we wrote the definition of the unions, we said X is where? Like, what X's are we checking? I mean, kind of innately, you would say, like, well, the X is in, I don't know, either A or B, right? But I guess you mean the X is in the union. And we shouldn't use the union to define what the union is, right? Oh, no. It seems in some sense that we're actually assuming that X is in some sort of a universal set to which both the elements of A and B belong. Yeah? Similarly here. Okay, so this is perhaps fine, but you can imagine in similar ways to how we ended up with troubles from unrestricted comprehension, that is when we said, hey, can I just define sets via predicates? And the answer was, no, you got to be careful, right? Otherwise you end up with situations like the set of all sets that don't contain themselves, which, is it a set? Does it belong to itself or does it not belong to itself? You get a contradiction, right? Either one of those results in the other thing. And you can't have both. So similarly, there is perhaps here a little bit of not care being taken. For most of the sets that we're talking about, this is a relatively easy thing to get past. That is, when we start going, hey, you've got A and B, two sets, we could immediately presume perhaps that these sets belong to some universe, right? And then from that, we could get the union by taking the elements in the universe that are either in A or in B. So perhaps this is somewhat saved by saying, well, if we're going to talk about our sets in the first place, we could talk about some universe to which they belong. But I guess what I'm trying to point out is that there are details here that are effectively being swept under the rug, mostly as an appeal to our regular old intuition. But if you push some of these things further, you can end up with issues. That is, there is still floating around in the background this lingering doubt about what is the universe that we're talking about? That is, where are all of these things living? Are we running into problems if we pick things, our universe poorly? It's a good question. Fortunately, it's not something you have to care about for nice and easy things like finite sets. It's relatively easy to construct a universe for, sets of numbers up to 10, right? Let's let the universe be the numbers 1 through 10, or 1 through 100, or 1 through 10, and also the number 14, right? Pick whatever one you want. You can define it in those situations, and you can make perfectly good sense of it. But if we start dealing with bigger sets, perhaps we might run into a little bit more trouble. Or if perhaps our sets themselves contain sets or are like crazy, have like self-referential statements, perhaps even basic definitions like this start to break down. So I guess my point is that there is complication here that we are somewhat brushing under the rug for right now as we get used to it in a familiar setting. But there is a specter lurking in the background as we get close to October. Some sort of a Halloween theme of there's spooky problems at work here. Okay, so a quick little theorem to end the day. That clock only keeps getting more and more off. I have 7 minutes, but according to the clock, I have 30. Oh boy. So we'll do 30 minutes of work in 7. No, we'll write a theorem. We'll talk about it briefly. We'll prove some stuff from it next time and recall it. Okay. So here, theorem, let A, B, and C be any sets in the universal set U. Then we get the following. So I made the small digression about universal sets because this, otherwise might seem kind of weird. Why am I talking about a universal set here? But basically, you have to somehow specify this first. And perhaps if you specify it badly, things might get messed up. But for now, all right, we've got a universal set U. Then we get the following. 1, these are the commutative laws. You get that A union B is equal to B union A, and B, A intersect B is equal to B intersect A. Okay, you do it whatever order you want. That's kind of nice. All right, 2. Get the associative laws, which tell you that, well, first off, A union B intersects C is equal to A union B intersect C, and B, that A intersect B union C is equal to A intersect B union C. Okay. 2. Now, we just have a few more. You get the distributive laws, which tell you that, well, 2 statements yet again, that if you take A union B intersect C, this is the same as A union B intersect A union C. Likewise, A intersect B union C, well, this is A intersect B union A intersect C. Cool? See how they're basically the same, just flipping cups and, yeah?
The associative laws on the paper look a little different.
Wait, did I write my associative laws wrong because I'm trying to go fast? Oh, no, I did. I was getting to the wrong place, and that is actually not, okay, here. Sorry, I've made a mistake. Forgive me. The clock has foiled me again. I've written something wrong by going fast. This says that A union B union C is indeed equal to A union B union C, and A intersect B intersect C is A intersect B intersect C. When I say it out loud, it sounds like I'm saying the same thing twice. The parentheses make all the difference. It just says it doesn't matter which order you do it in. Cool? Okay, I've made a mistake and I apologize for that. I hope I didn't seriously confuse anybody. I'm glad I typed these up because it makes it more clear. You have idempotence, which tells you that, well, A union A is in fact equal to A, and B, that A intersect A is in fact equal to A. And then finally, you have the identities. That is, there are identity elements. A says that A union the empty set is indeed equal to A, and B, A intersect the universal set is indeed equal to A. Okay, cool. So, a lot of different pieces here, but all of it boils down to telling us that we've got relatively nice and well-behaved operations that work pretty similarly to our good old-fashioned rules of arithmetic. That is, just like addition, it doesn't matter what order you do unions in. Same thing with intersections. You can do a pair of unions amongst a triple of things in whatever order you want. Same with intersections. You can take a union and you can distribute it across an intersection, and you can take an intersection and distribute it across a union. The one that I accidentally wrote over here was in fact wrong, and we'll talk about what the correct statement is about an intersection of a union or a union of an intersection. And we'll talk about that soon. We will not talk about it today because we only have perhaps 1 or 2 minutes remaining. And I imagine we can just leave it there, touch on this next time, do some proofs. I'll see you around. Have a wonderful Wednesday, and I'll see you on Friday.